The year is 1610. A man in Italy points a homemade telescope at a pale yellow light in the night sky, and he sees something that does not make sense. It isn't a single planet. It looks like three, a large round body in the middle, and on either side, two smaller shapes pressed right up against it, never changing with respect to one another. The man writes to the Duke of Tuscany that the planet Saturn is not alone. He calls the two shapes ears, companions. He doesn't have a word for what he is looking at, because no human being has ever seen it clearly before. His name is Galileo Galilei, and he has just become the first person in history to look directly at the rings of Saturn. And then, 2 years later, they disappear. In 1612, Galileo turns his telescope back to Saturn, and the ears are gone. The companions have simply vanished, as if they had never been there at all. He is stunned. He writes that he does not know what to say in a case so surprising. And then, almost as a dark joke, he asks the question that hangs over this entire story. Has Saturn swallowed his own children? A year later, the children come back. Galileo died not knowing what he had seen. And for 400 years after him, we kept making the same quiet assumption he did that this calm, glowing jewel was exactly what it appeared to be. Serene. Eternal. It is none of those things. Because those vanishing rings were the first sign of a habit this planet has never broken, it shows us only what it wants us to see. And in just the last few years, as our instruments have finally grown sharp enough to look beneath the surface, we have begun to find what the rings have been concealing the whole time. They are not as old as the planet they circle. They are not made of what we were told, and they are not even staying. The truth about Saturn's rings is not the one in the photographs, and the closer we look, the less comfortable that truth becomes. For decades after Galileo, the rings stayed a riddle. It took almost 50 years before someone finally explained what those vanishing ears really were. In the 1650s, a Dutch astronomer named Christiaan Huygens, grinding his own lenses with his father and building a telescope more powerful than anything Galileo ever had, became the first person to suggest the truth. Saturn, he wrote, is surrounded by a thin, flat ring, nowhere touching the planet, and tilted relative to its path around the Sun, a detached floating disk. That single idea explained the disappearing act. The ring hadn't been swallowed. It had simply turned edge onto us, so thin that from this distance it became invisible and then tilted back into view. The children that Saturn devoured were never gone. We were just looking at them sideways. Now here is where the story usually gets handed to us as settled. Huygens found the ring. A generation later, in 1675, the astronomer Giovanni Cassini looked closer and discovered that it wasn't one ring at all. It was many smaller rings, with gaps between them. The largest of those gaps, a dark lane nearly 5,000 kilometers wide, still carries his name today, the Cassini division. And from there, the rest seemed to fall into place. In the late 1700s, Pierre-Simon Laplace proved that a single solid ring would tear itself apart, so the rings couldn't be solid sheets. In the 1800s, James Clerk Maxwell went further and showed that the rings had to be made of countless tiny particles, each one independently orbiting the planet on its own. By the end of that century, astronomers splitting Saturn's light through spectroscopes confirmed it. The rings were not a solid object. They were a storm of separate pieces, a billion tiny moons, all circling together. That is the version most of us were taught. A beautiful, settled, finished picture. It's not wrong, exactly, but it's the surface. It's the ears that Galileo saw before anyone understood what they were looking at. And underneath that tidy story sit two genuine mysteries, one about how fast this planet is turning, and one about what its rings are quietly made of that took us until this past decade to even begin to crack. And the man at the center of one of them spent the better part of his career being told, by his own data, that the answer was impossible. His name is Tom Stallard. He is a professor of planetary astronomy, and for years he has been chasing one of the longest-standing puzzles in all of planetary science. The question sounds almost too simple to be hard. How fast does Saturn spin? On Earth, that's an easy thing to answer. You watch a feature on the surface, a mountain, a coastline, and you time how long it takes to come back around. One rotation. Done. But Saturn doesn't have a surface you can see. It's a giant world of gas and cloud, and the cloud tops slide around at their own speed, faster at the equator, slower near the poles. So to find the true rotation rate, the spin of the planet itself, deep down scientists had to use a different trick. They listened to its radio pulse. Like several other giant planets, Saturn beams out a rhythmic pulse of radio energy, a kind of cosmic lighthouse beam that sweeps past us once per rotation. Count the beats, and you've timed the planet's day. It's the same method used to clock the spin of Jupiter, of Uranus, of Neptune, even of dead stars and distant brown dwarfs far outside the solar system. The radio pulse is the heartbeat. And for a planet, that heartbeat is supposed to be one of the most reliable, unchanging numbers there is. Then, in 2004, NASA's Cassini spacecraft arrived at Saturn and started counting the beats, and the number had changed. Stop on that for a moment, because this is the fact that broke the field open. Measurements taken by Cassini suggested that Saturn's rotation rate was slowly changing over time. The length of Saturn's day appeared to be drifting, and that should be impossible. A planet is a colossal object. You cannot simply speed up or slow down the spin of an entire world the way you'd nudge a bicycle wheel. There is nothing to push against, and the energy involved is staggering. A planet's spin is supposed to be one of the most fixed quantities in nature. Yet here was Cassini, sitting in orbit around Saturn, reporting that the beat was getting slower. Over 4 years of watching, the northern radio period stretched out, lengthening measurably, while the southern half of the planet kept a different time entirely. 2 hemispheres, 2 clocks, neither one matching the other, and both of them appearing to drift. So what does that mean? Either we had discovered a planet that was somehow changing its own rotation, rewriting the textbooks, or we were measuring the wrong thing entirely. And in 2021, Tom Stallard showed it was the second one. His study revealed that the mystery had nothing to do with Saturn's rotation at all. The planet wasn't speeding up or slowing down. Instead, the misleading signal was being created higher up by winds in Saturn's upper atmosphere. Those winds were generating electrical currents, and those currents were warping the very radio pulse that everyone had been using as the planet's heartbeat. We hadn't been timing Saturn's spin. We had been timing the weather in its sky and mistaking it for the turning of the world. It was a genuine breakthrough. It dissolved the impossible problem, and it should have been the triumphant end of the story, except it wasn't. Because the moment Stallard answered one question, the data turned around and asked him a harder one. If atmospheric winds were faking the planet's spin, then what was driving the winds? He had solved the mystery. And in solving it, he had simply moved it deeper into the planet, somewhere he couldn't yet reach. For years, that's where it sat. He knew something strange was happening in Saturn's atmosphere. He had proven it was real, and he still had no way to explain why. What he needed was a way to see the upper atmosphere of Saturn in detail no one had ever managed before, and the instrument that could finally do it had only just opened its eyes. To understand how this mystery was cracked, you have to understand a single, strange molecule. High in Saturn's upper atmosphere, far above the clouds, there is a molecule called trihydrogen cation. It forms naturally up there, and it has a remarkable property. It glows in infrared light, and the exact character of that glow depends on how hot it is. Heat it up, and the light it gives off shifts. Cool it down, and it shifts again. In other words, this molecule is a thermometer, a natural, glowing thermometer suspended in the sky of another planet, broadcasting the temperature of Saturn's atmosphere out across the solar system for anyone with a sensitive enough instrument to read it. The trouble was, nobody's instrument was sensitive enough. Saturn's version of this glow is faint, far fainter than the same molecule's glow at Jupiter, and for decades, reading it in any detail was simply beyond us. We had first detected the molecule at Saturn back in 1992, but the best maps anyone could make were blurry, smeared-out averages, combining huge regions of the planet into single, smudged readings. Those old measurements carried errors of around 50 degrees, which was a disaster, because the temperature differences scientists were hunting for were themselves only about 50 degrees. It was like trying to measure the thickness of a coin with a ruler marked only in centimeters. The thing you were looking for was the same size as your margin of error. Then came the James Webb Space Telescope, the most powerful space telescope ever built, an international observatory led by NASA with its European and Canadian partners. On the 29th of November, 2024, Webb turned its infrared eye on Saturn's northern pole, and it didn't just take a snapshot. It watched continuously for an entire Saturnian day, roughly 10 hours, tracking the planet through one complete rotation. At that moment, Saturn was in its late northern summer. The pole tilted clearly toward us, approaching an equinox that would arrive the following spring. The timing gave Webb a clean, uninterrupted view of the planet's northern lights for the very first time. And the detail it captured was extraordinary. Where the old maps could resolve nothing finer than vast, blurry zones, Webb could pick out features smaller than 500 kilometers across. Its measurements were roughly 10 times more accurate than anything that had come before. For the first time in history, scientists could draw a true, high-resolution map of both the temperature and the density of Saturn's aurora strand by strand. Hot filament beside cold filament. The way you'd map weather across a continent instead of guessing the climate of a whole hemisphere from a single number. When that map appeared, it revealed something nobody had ever seen at Saturn. The aurora was not evenly spread. The heat was lopsided. One side of the auroral region was distinctly hotter than the other, with the warmest zone and the coldest zone sitting in near-perfect opposition across the pole. A temperature difference of around 150 degrees stretched across the whole region, with the planet's atmosphere running, in the hottest patches, to a little under 500 degrees on the Kelvin scale. And here is the part that mattered. That strange, lopsided pattern of heating and cooling matched something. More than a decade earlier, scientists had built computer models predicting what Saturn's aurora should look like if a very specific idea were true. Those models had sat there for years, untested, because no instrument could check them. Now Webb checked them. And the real planet matched the old prediction almost exactly, but only on one condition. The match only worked if the source of the heat was placed precisely where the main auroral particles rain down into the atmosphere. That single condition is the whole answer. Let me unpack what it means. It means Saturn's aurora is not just a light show. We tend to think of the northern lights here on Earth, or on any planet, as something beautiful, but essentially passive. A glow painted on the sky by particles falling in from space. But at Saturn, the aurora is doing something. It is actively heating the atmosphere, and it is doing it in one specific place. And once you have heat in one specific place, physics takes over. Heat creates a temperature difference. A temperature difference drives winds as the atmosphere flows away from the hot spot. Those winds drag the electrically charged particles of the upper atmosphere along with them, and moving charged particles are, by definition, an electrical current. And that current, feeding back into the planet's magnetic environment, is exactly what powers the aurora. Do you see what that is? It's a loop, a circle with no beginning. The aurora heats the atmosphere. The heat drives the winds. The winds generate the currents. The currents power the aurora, which heats the atmosphere, which drives the winds. Around and around and around. The lead researcher described it in one perfect phrase. What we are seeing, he said, is essentially a planetary heat pump. Saturn's aurora heats its atmosphere. The atmosphere drives winds. The winds produce currents that power the aurora, and so it goes on. The system feeds itself. The system feeds itself. After decades of chasing a planet that seemed to be changing its own spin, this was the thing at the bottom of it, a self-sustaining engine running in Saturn's sky, generating the very winds that had been faking the planet's heartbeat all along. These new observations, the team said, finally gave them the evidence they needed to close the loop. And there's a quiet detail worth holding on to here, because it will matter later. The engine doesn't stop at the edge of the atmosphere. The currents it generates reach outward, into the vast magnetic bubble surrounding the planet, and that region feeds energy right back down into the atmosphere again. The sky and the space around Saturn are locked together in a two-way exchange, and that constant feedback may be exactly why this whole strange system is so stable and so long-lasting. It's worth pausing on what this tells us about the planet itself. Webb was watching the sky, the thin, electrified, outermost shell of Saturn, but that shell is keeping a secret about the world beneath it. Because deep down, far below all of this, the true planet really is turning at its own steady rate, a genuine rotation of about 10 hours, 32 minutes, and 45 seconds. We even know that the giant six-sided storm at Saturn's North Pole, the famous hexagon, has held its own rhythm with astonishing discipline, drifting by a mere 3 seconds across the 30-odd years between the Voyager flyby of 1980 and the end of the Cassini era in 2014. So the planet has a true heartbeat. It always did. The aurora was simply singing over the top of it, loudly enough to drown it out. And for decades, we listened to the wrong voice. That should be a tidy ending, a loop closed. But the people who study this planet have learned the same lesson Galileo learned in 1612. With Saturn, the moment you think you've seen the whole thing, it turns edge on and shows you that you were only ever looking at the surface. Because the rings, the part everyone thinks they understand, were quietly hiding the strangest secret of all. And, to find it, a spacecraft had to fly somewhere no spacecraft had ever been. In 2017, after 13 years orbiting Saturn, the Cassini spacecraft was running out of fuel. Rather than let it drift and risk crashing into one of Saturn's potentially habitable moons, NASA chose to end the mission on its own terms and to spend its final months doing something genuinely reckless. They flew it through the gap. Between the inner edge of Saturn's rings and the top of the planet's clouds, there is a narrow opening. Across roughly 5 months in 2017, from April to September, Cassini dove through that opening 22 separate times, threading the needle between the rings and the planet at tremendous speed. They called it the grand finale, and it put the spacecraft, for the first time ever, directly in the path of material falling out of the rings and down into Saturn. Now, Cassini was carrying an instrument built for exactly this moment, the Cosmic Dust Analyzer. It works by catching individual grains of dust as they slam into a target plate. At these speeds, the particles were hitting at around 30 kilometers every second, faster than any rifle bullet. Each impact vaporizes the grain into a puff of charged atoms, and the instrument reads that puff like a fingerprint, identifying exactly which elements the grain was made of. It is so sensitive that it can analyze a particle only a few tens of nanometers across a speck so small that millions of them would fit on the head of a pin. Over those final dives, the instrument caught more than 1,000 of these grains streaming out of the main rings and falling toward the planet. And when scientists later sorted through them and pulled out the ones that were tiny shards of rock, the silicate particles, the non-icy material, they found something they were not expecting. Here's the background you need. For a long time, the assumption about Saturn's rings has been clean and simple. The rings, everyone agreed, started out as nearly pure water ice, and over millions of years, they slowly got dirty colored, as the researchers put it, by an endless drizzle of dust falling in from deep space. Interplanetary dust particles, the gritty debris that drifts through the solar system, were thought to be raining onto the rings and gradually contaminating them with rock and metal. That infalling dust was supposed to be the main source of all the non-icy material in the rings. So, when Cassini sampled the rock falling out of the rings, scientists expected it to look like that incoming space dust. Same recipe, same ingredients. It didn't. And the difference came down to a single element: iron. The rock falling out of Saturn's rings was strangely poor in iron. The grains were rich in magnesium and silicon and calcium, in proportions close to the cosmic baseline you'd expect, but the iron was missing, depleted, on average, well below the normal cosmic amount. And when the team compared this ring material directly against the actual interplanetary dust that Cassini had measured drifting through the Saturn system over its 13 years, dust collected by the very same instrument, so the comparison was airtight. The gap was stark. The incoming space dust was something like 5 times richer in iron than the material coming out of the rings. There was an entire family of iron-rich grains in the infalling dust that was simply absent from the ring debris. Gone. Sit with how strange that is. If the rings are just made of accumulated space dust, then the stuff falling out of the rings should look like the stuff falling into them. It doesn't. The recipe has changed. Somewhere in the rings, the iron is being removed. So what's happening to it? The researchers laid out the possibilities carefully, because this is exactly the kind of puzzle where it's easy to fool yourself. Maybe the dust we're seeing fall in today isn't representative of the dust that built the rings over millions of years. Maybe there's a hidden selection effect where iron-rich grains get sorted out before they ever reach the spacecraft. But the explanation they found most convincing is the most unsettling one, because it means the rings are not a passive archive at all. They are a chemical factory. When a grain of iron-rich space dust comes screaming into the rings and smashes into one of the icy ring particles at those enormous speeds, it doesn't just stick, it vaporizes. And in that flash of heat, surrounded by water vapor blasted off the ice, the iron undergoes a chemical change. Instead of staying as the metal or the sulfide it arrived as, it is converted, locked up into iron oxides, heavier, different, and crucially, left behind. The lighter, iron-poor rock gets flung onward and eventually rains down into Saturn, which is what Cassini caught on its way through the gap. But the iron stays in the rings, accumulating, hidden, slowly building up over geological time as a growing reservoir of dark iron oxide that we cannot easily see. In other words, the rings are eating the iron. They have been quietly hoarding it, hiding it inside themselves for longer than there have been humans to wonder about them. And the bright, innocent, icy rings that Galileo mistook for ears are underneath, in the middle of a slow chemical transformation we are only now beginning to read. There was even a clue hiding in the ice itself. Separate observations found that the water ice in Saturn's main rings is almost entirely crystalline. That sounds like a small detail, but it isn't, because over long ages, constant radiation should have scrambled that ice into a disordered, amorphous form. The fact that it's still neatly crystalline hints that the ring material is being repeatedly heated and reworked, exactly the kind of violent recycling that the iron story requires. The rings aren't sitting still, they're being stirred. While one team was reading the chemistry of the rings, something else was quietly getting stranger about Saturn. We kept losing count of its moons. For most of history, Saturn's moons were discovered one at a time, and often by accident found in those rare moments when the rings turned edge on and went dark, letting faint objects nearby finally show themselves. That's how Cassini himself spotted several of them in the 1600s. One careful discovery, then a long wait, then another. That trickle has now become a flood. In May of 2023, astronomers announced 64 new moons of Saturn at once. Less than 2 years later, in March of 2025, they announced a staggering 128 more. And then, on the 16th of March, 2026, the Minor Planet Center, the international clearinghouse that officially confirms these things, announced another 11. That last announcement pushed Saturn's confirmed total to 285 moons. 285. For comparison, Jupiter, the largest planet in the solar system, sits at 101. Saturn has nearly 3 times as many and holds a commanding lead as the moon capital of the solar system. But the number isn't the strange part. The strange part is what these moons are. The vast majority of them are not the great worlds you've heard of, not Titan, the moon larger than the planet Mercury, not Enceladus with its global ocean hidden under ice. They are tiny, dark, irregular chips of rock, many only 1 or 2 kilometers across. They are so faint, around 100 million times dimmer than anything the naked eye can see, that out of all 285, only 64 have earned proper names at all. The rest are known by strings of letters and numbers, designations rather than names, because the rules say an object this faint only gets a name if it's of special scientific interest. So why are we suddenly finding so many? Not because they're new. They were always there. They were simply too small and too dim for us to catch until our eyes got sharper. A new observatory came online in 2025, a machine so sensitive to tiny changes in the sky that on a single night it can issue hundreds of thousands of alerts about objects shifting and moving against the stars. Astronomers learned to combine old images with new ones, hunting for the faint specks that drifted, and the moons came pouring out of the dark. And here's the image that captures the scale of it. Saturn's swarm of moons is spread so far and wide that, seen from Earth, the entire entourage covers a patch of sky about 5 times as wide as our own full moon. Picture standing under that ringed planet and seeing its family of satellites stretching out for an enormous distance on either side, most of them invisible, all of them there. Saturn has been carrying a crowd this whole time. We just couldn't see them. Here is something the simple picture leaves out. When you look at Saturn through a backyard telescope, you see what looks like one smooth, glowing band, maybe split by a single dark line. But that smooth band is an illusion of distance. Up close, the rings are not one ring, and they are not simple. They are a vast, intricate piece of architecture, and the unsettling thing is that nobody built it. We've actually named the major rings, and we did it in the clumsiest possible way, in the order we happened to discover them. So the lettering makes no sense as you travel outward. Working out from the planet, the main bright rings are the C ring, then the B ring, then the A ring, with the Cassini division, that famous dark gap separating the outer two. Closest of all to the cloud tops is the faint D ring. Just beyond the A ring sits the narrow F ring, and further out still are the ghostly G and E rings. The order they sit in, and the order we found them, have almost nothing to do with each other, a small monument to how piecemeal our understanding of this planet has always been. But the real revelation is what holds all that structure in place, because those gaps between the rings are not random, and they are not empty accidents. They are being actively carved and held open by Saturn's moons. Take the Cassini division, that nearly 5,000-kilometer lane that Galileo's successors first spotted from Earth. For a long time it looked like a simple empty stripe. It is nothing of the kind. It exists because of the moon, Mimas. Any ring particle drifting into that gap finds itself orbiting Saturn almost exactly twice for every single orbit Mimas makes. That rhythm matters. It means Mimas tugs on those particles at the same point, over and over, and those tugs add up until the particles' orbits become unstable and they are swept clear. The gap is not an absence. It is a scar, kept open by the steady gravitational drumbeat of a distant moon. Now look closer, into the gaps within the rings themselves, and it gets stranger. Inside the A ring there is a clean lane called the Encke Gap, and sitting right in the middle of it, sweeping it clear, is a tiny moon named Pan. There is a second, narrower lane nearby called the Keeler Gap, and inside that one rides an even smaller moon, Daphnis. And here's the detail that turns physics into poetry. The orbit of Daphnis is tilted just slightly out of the ring plane. So as it travels, its gravity doesn't just push the ring edges sideways, it lifts them. Daphnis raises standing waves along the walls of its gap that rise as much as 1,500 meters above the otherwise flat rings. And during Saturn's equinox, when sunlight strikes the ring's edge on, those waves throw long shadows across the ice. A moon the size of a small mountain, casting the shadow of the waves it makes across a structure thinner than a sheet of paper. The same thing happens at the very outer edge of the Great B Ring. There, hidden moonlets we cannot even see directly betray themselves through vertical walls of ring material standing up to 2.5 kilometers high, towering by the standards of a ring that is normally just 10 meters thick. We know the moonlets are there only because of the structures they raise and the shadows those structures cast. And then there is the F ring, which may be the strangest of all. It is the outermost of Saturn's distinct, narrow rings, and it is the most restless object of its kind in the entire solar system, a ring whose appearance can change, not over centuries, not over years, but over the course of hours. It is shepherded by a pair of small moons, Prometheus and Pandora, riding just inside and outside it. As Prometheus swings closest to the ring on each orbit, its gravity reaches in and steals material, gouging a dark channel into the ring's inner edge. And because the moon races around the planet faster than the ring does, every new channel it carves appears a few degrees ahead of the last, leaving the F ring laced with a repeating, drifting pattern of kinks and gaps, constantly being rewritten. But the most haunting feature in the rings is one we still cannot fully explain. Until 1980, the consensus was total. The structure of Saturn's rings was the work of gravity, and gravity alone. Then the Voyager spacecraft sent back images of the B ring, and there were marks on it that gravity could not account for, dark, radial streaks reaching across the ring like the spokes of a wheel. They were named, simply, spokes, and they made no sense. They rotated around the rings in a way that orbital mechanics forbids. Particles closer to the planet should circle faster than those farther out, smearing any such feature into nothing within hours. Yet the spokes held their shape. The leading explanation is that the spokes aren't made of orbiting boulders at all, but of microscopic dust particles so fine they are lifted up off the ring plane by electric charge, hovering above the ice and turning almost in lockstep with the planet's magnetic field instead of with the rings beneath them. But the precise mechanism that creates them is still, to this day, unknown. We know only that they come and go, with the Saturnian seasons fading away near midsummer and midwinter, returning as the planet approaches its equinox. After Voyager first caught them, they vanished for a quarter of a century and were not seen again until the Cassini spacecraft finally photographed them once more in 2005. A planet that grows ghostly streaks on its rings, on a schedule we can predict, but by a process we cannot name. That is the level of mystery we are still dealing with, not in some distant galaxy, but on the most photographed object in our own solar system. There's even an atmosphere out there. The rings, it turns out, are wrapped in their own impossibly thin envelope of oxygen gas, created when sunlight breaks apart the water ice and frees it. If you could somehow collect that entire ring atmosphere and press it down onto the ice, it would form a layer about 1 atom thick, a breath of air around a structure made of shattered ice, sculpted by moons, streaked by shadows we don't understand. None of it was designed. All of it is balanced on the edge of chaos, and every piece of it is temporary. To really feel how unsettling Saturn is, you have to get the scale right, and Saturn's scale is almost designed to deceive you. Start with the rings, because the numbers genuinely don't sound like they belong to the same object. Saturn's ring system stretches across roughly 282,000 kilometers. That is a structure wide enough that you could line up dozens of Earths across it. It is, by far the most enormous and elaborate ring system of any planet in the solar system. Now here is the part that breaks your intuition. That vast, sweeping disk, hundreds of thousands of kilometers across, is almost unbelievably thin. In most places, the rings are only around 10 meters thick. 10 meters. The height of a few people standing on each other's shoulders. Try to actually hold both of those facts in your head at once, because it's nearly impossible. Imagine a sheet of paper. Now, imagine that sheet of paper is the size of a city, and yet still exactly as thin as ordinary paper. That is closer to the true proportions of Saturn's rings than anything your mind wants to picture. They are spread across a width that dwarfs entire planets, and they are flatter, relative to that width, than any sheet of material you have ever touched. That is why they vanished on Galileo. Turn a structure that thin, even slightly edge on, across 1 billion kilometers of empty space, and it disappears completely. And for all that breadth, the rings weigh almost nothing by Saturn's standards. When Cassini made its final dives through the gap, it didn't just sample the dust. It felt the gravity of the rings directly and measured their total mass. The answer came out to roughly 4/10 the mass of Mimas, one of Saturn's smaller moons. To put that in earthly terms, the researchers offered a comparison that lands with real force. The entire ring system holds about 2/3 as much material as Earth's whole Antarctic ice sheet, except smeared across a surface 80 times larger than our entire planet. That's the truth the rings conceal behind their brightness. They look solid, they look permanent, they look heavy. They are none of those things. They are a colossal, gossamer-thin veil of countless ice particles, almost weightless for their size, held in a perfect circle around a world that has been quietly transforming them from the inside. And against that backdrop, one last number starts to feel less like an astronomy fact and more like a warning. For most of human history, we assumed the rings were as old as the planet. It seemed obvious. Something so grand, so perfect, so much a part of what Saturn is, surely it had been there since the beginning, 4.5 billion years ago, and would be there long after we were gone. The data from Cassini suggests we were wrong about all of it. The newest estimates, built on that final low-mass measurement and on the rate at which the rings are darkening as dust falls in, point to a startlingly young age. The rings may have formed only within the last 100 million years or so, possibly somewhere between 10 million and a few 100 million years old. Set that against the planet beneath them, and the contrast is staggering. Saturn is ancient. The rings, by comparison, are almost brand new. There may well have been a stretch of Earth's own history, the age of the great dinosaurs, during which Saturn had no rings at all. So where did they come from? The leading idea is also the most violent. The rings may be the shattered remains of a moon that wandered too close to Saturn and was torn apart by the planet's gravity, or one that was destroyed in a catastrophic collision. Recent simulations even gave that lost, hypothetical moon a name. They called it Chrysalis, a world that died and whose scattered body became the most beautiful structure in the solar system. But it's the other end of the timeline that should stop you cold, because the rings are not just young, they are disappearing. Remember the material Cassini caught falling out of the rings and down into Saturn? That isn't a one-time event, it is constant. Gravity is steadily pulling the icy particles of the rings down out of orbit, raining them into the planet, a process scientists have come to call, almost gently, ring rain. Ground-based telescopes measured this rain falling at a rate of hundreds, even thousands of kilograms every second. And when Cassini flew through the gap and measured the flow directly, the number was even larger, thousands to tens of thousands of kilograms of material pouring inward every single second. Run that forward, and the conclusion is unavoidable. At this rate, Saturn's rings have perhaps 100 million years left, maybe less. On the timescale of the solar system, that is the blink of an eye. The rings did not exist for most of Saturn's life, and they will not exist for most of what remains of it. which means something almost too strange to accept. Out of 4.5 billion years of this planet's history, out of all the vast, empty ages before us and all the ages still to come, we happen to show up, build telescopes, and look up during the narrow, fleeting window when Saturn has rings at all. Galileo turned his crude telescope to the sky in 1610 and saw two companions he couldn't name. He watched them vanish and asked if the planet had swallowed its children. He was closer to the truth than he ever knew. The children are falling in. The rings are being swallowed slowly, particle by particle, in a rain we can now measure. We just arrived early enough to watch it happen. We tend to call Saturn beautiful, and it is, but spend enough time with what the data actually says, and the beauty starts to feel like something else. A planet whose sky runs on an engine that feeds itself, drowning out the true turning of the world beneath. Rings that quietly devour the iron that falls into them and hide it in the dark. A swarm of moons too faint to count, stretching across the sky, and a crown of ice so impossibly thin and so impossibly young that it is already dissolving back into the planet that made it. None of that is terrifying in the way a monster is terrifying. It is terrifying in a quieter, larger way, the way it feels to realize that the most permanent, iconic thing in the night sky is in fact a brief accident of timing, and that we are standing in the one small moment when it exists. We learned how fast the planet truly turns. We read the chemistry of dust falling out of its rings. We counted moons we never knew were there. And the more closely we looked, the more clearly we understood a single, humbling thing, that we are not looking at something ancient and eternal. We are looking at something rare and changing and quietly coming to an end. And we got here just in time to see it.